So now before we wrap up divide and conquer, I want to go over one algorithm that has a really interesting connection with divide and conquer. And it is not an array algorithm. It looks nothing like the other divide and conquer algorithms we've looked at, but it falls into the framework perfectly, right? It exactly fits the divide and conquer framework in a really strange and surprising way. So the question here, algorithmically, is how do we multiply large integers? And so, we'll play with small integers, two or three digit integers today in our examples. But what we're really talking about is in the hundreds of digits, right? So we're talking about integers that are something like RSA keys. An RSA key should be at least 2,000 bits, say. If it's 2,000 bits, I think that's something like 300 decimal digits. So there we're talking, right? So we're talking about numbers that are way too big to be referring to any physical quantity, but that are large enough that they'll give us some strong cryptographic guarantees or something like that. So these are real things, right? These are actual numbers that we care about because of things like RSA. But they're not numbers that we'll use to describe actual things. Anyway, the question is how do we multiply large integers, and is there a fast way to do this? Right? RSA is all about multiplying large integers. Right? You have to do that to be able to encrypt and decrypt RSA. So let's figure out how to do it. So let's do a small one. Let's multiply 23 by 14. And think about how we as humans would do this. And so now we're gonna run back in time to 4th grade or 7th grade or whenever it is you learn this stuff, to one of the very first algorithms all of us learned, and that's this long form multiplication thing. So I'm gonna write 23 on top of 14, and I'm gonna multiply. Right? How do you do this? Well, first I multiply 3 by 4. Okay, if I multiply 3 by 4, what do I get? Well, I get 12. So I write the 2 there, the 1's digit there, and then I write the 1 up there. So you didn't know you were learning an algorithm when you learned this, but this is an algorithm, and it works, right? So 3 times 4 is 12. I got the 1 there, I got the 2 there. 2 times 4 is 8. I add that 1, and so now I have 9 there. Okay, so then I take 1 times 3, and that gives me 3. And then 1 times 2, and that gives me 2. And then I just add these two numbers together, right? So I drop my 2 straight down. 9 plus 3 is 12. And so there I've got my 12 here, and I carry the 1. And then I add 1 and 2, and I get 3. Right? So there we have it. In my head, I just multiplied, not in my head, on paper, I just multiplied 23 by 14, and the answer is 322. So let's think a little bit about what we just did, right? How many multiplications did we perform? Well, we multiplied 3 by 4. So I'll track these in red. We multiplied 3 by 4. Then we multiplied 2 by 4. Then we multiplied 1 by 3. Then we multiplied 1 by 2. Okay, so altogether, there's 4 multiplications. Okay, and then you could track how many additions as well, but it's a little bit less clear to do it like this. Instead, let's kind of write this out in a long form. Right? Let's write down a little bit of a description of why this algorithm works. All right, so I'm gonna write 23. Right, so there's our long multiplication. Now let's think about what's going on underneath the hood here. So 23 times 14. I can rewrite in the following way. So I can write this as 2 times 10 to the power of 1. I'll just call it to the power of 1. Plus 3 times 10 to the power of 0. Right? So this is the number 23 that I've just written out. That's just the definition of 23. Right? This is just what it means to write something down in decimal. Okay, so I want to take that thing and multiply it by 1 times 10 to the 1 plus 4 times 10 to the 0. Okay, so this is just sort of writing down stuff we already know, right? This is just writing down a whole bunch of kind of annoying stuff. And so now let's think about if we were to actually cross multiply this stuff, or if we actually were to work this out in detail, what would we get? Well, we'd get this. We have these two terms multiplied together. So that's 2 times 10 to the 2. Okay, so that's those two. And then we have these two terms, oh, sorry, I just did that. We have these two terms multiplied together. So that's plus 2 times 4 times 10 to the 1. And then, just to skip a step, I'll add in this. So 2 times 4 plus 3 times 1 times 10 to the 1. And then plus 3 times 4 times 10 to the 0. Okay? And so what do I have? It's 2 times, I'm just make sure that I'm being totally exhaustingly complete here. So what do I have? Well, I've got all my multiplications written down now, right? So I've got this multiplication, I've got this multiplication, and this multiplication. So the observation we can make is if I multiply together two two-digit numbers, I can accomplish that by multiplying together four-digit numbers. Okay, so I perform 4 one-digit multiplications to do 1 two-digit multiplication. Okay, so 4 one-digit mults to do 1 two-digit multiplication. Okay, so now let's kind of dig into this just a little bit. Let's look a little bit more closely at what's going on. Okay, so let's look at this. Okay, let's think about if there's a way we could optimize this. So if I write this stuff here, so 2 times 4 plus 3 times 1. Here's my interesting fact that I will demonstrate to you. I'll show you why this is true. So here's my interesting fact. 2 times 4 plus 3 times 1 can be written as 2 plus 3 times 1 plus 4 minus 2 times 1 minus 3 times 4. Okay, so I recognize that it's not yet clear why this matters, but bear with me just a moment, and we'll work it out. So just before we show what it's for, let me just make sure that you believe it's true. So I have this expression on the left, I have this expression on the right. I am claiming that they're both equal, that they're equal to each other always. Let me just show you that they're equal, and I'll show you this by just multiplying through everything on the right. So on the right, what do I have? I have 2 times 1 plus 2 times 4 plus 3 times 1 plus 3 times 4. Right? That's all of this together. And then minus those negative terms, 2 times 1 minus 3 times 4. So what do we see? Well, we see some cancellations. So I've got a minus 2 times 1, a plus 2 times 1, so those go away. I've got a minus 3 times 4 and a plus 3 times 4, so those go away. And then this matches that term, and this matches that term. Okay, so these two statements are equal to each other. Okay, so why would we care? Well, suppose we're trying to minimize the number of multiplications we do. Right? Suppose we're trying to do as few, we're regarding multiplication as costly, and we're trying to reduce the number of multiplications that we are required to perform. Well, my claim is that this expression, which notice only contains 3 multiplications, right? 1 here, 1 here, and 1 here, that this expression contains all the multiplications that are required to multiply 23 by 14. Okay? And so notice this. Here I've got my first blue arrow here is one-digit multiplication. Right? I've just added together 2 one-digit numbers and multiplied them. So it's a one-digit multiplication. And then the second blue arrow is a one-digit multiplication. third blue arrow is a 1-digit multiplication. And the whole thing together, right, if I add up all those terms, that gives me this, right? And then here my 3 times 4 gives me this, and my 2 times 1 gives me this. And this expression here captures all the multiplications, captures everything we need to multiply 23 by 14. Okay? So if I'm clever about which multiplications I do, it appears that I can actually get away with only 3. With just 3 multiplications between 1-digit numbers, 3 1-digit multiplications, to multiply 2 2-digit numbers together. Okay? Whereas the algorithm that we all learned way back in the day actually requires us to perform 4 1-digit multiplications. So the question is, can this be generalized? Right? So this has only, so the idea here is only 3 1-digit multiplications are required to multiply 2 1-digit numbers. Sorry, 2 2-digit numbers. Okay, so let's think a little bit about why that might be the case in the next video, and then more importantly, let's think about how we might generalize that.